Hi, it's Ms. Lenorovitz, and this presentation is going to go through an example of how to do ecosystem energy problems. So one of the important things that you need to know when you're doing any of your calculations in AP Environmental Science, and this is actually true and helpful in any setting, is that you're going to need to be comfortable and familiar with metric prefixes. So the ones that are highlighted on this screen, from 10 to the 12th down to the 10 to the negative 12th, are the typical metric system prefixes that you're going to need to know and apply. So they're going to be an assumed thing on the AP exam, and they're going to make your life a lot easier if you memorize them. So if you don't already know these prefixes, I encourage you to spend a little bit of time memorizing them. So 10 to the 12th is tera, 10 to the 9th giga, 10 to the 6th mega, 10 to the 3rd kilo, 10 to the 2nd hecto, 10 to the 1st deca. 10, of course, is the base number. And then if you're going to negative exponents, so here you'd be talking about 1 over 10 or 1/10. Some of these would be deci, 1/100th would be centi, 1/1000th would be milli, 1/1,000,000th would be micro, 1/1,000,000,000th would be nano, and then 1/1,000,000,000th would be pico. So we're going to be dealing with very large and very small values throughout this course. So those are the ones that you're going to need to memorize. In terms of scientific notation, I also want to remind you of a couple of rules so that you can apply scientific notation in a way that's going to help you do calculations. You will have access to a calculator on the AP exam, but you can also save yourself a lot of time and headache and a lot of math errors if you actually use scientific notation. So a couple of things that you probably already know. First of all, when you are expressing something in scientific notation, remember you're starting with a value that is between 1 and 9.999, and you're multiplying it by 10 to a power. So in this case, we're looking at 1 times 10 to the 6th. Remember, if your exponent is positive, that means you're dealing with a really large number. In this case, 10 times 10 times 10 times 10 times 10 times 10, or 1,000,000. Remember, if you see a negative exponent, that indicates that those values are in the denominator of your expression there. So this would be 1 over 10 to the 6th, or 1 over 1,000,000. The other things that you want to keep in mind for scientific notation, and this is where it can offer you some shortcuts, is if you're multiplying two values that are both multiplied by 10 to an exponent, in this case 10 to the 2nd times 10 to the 3rd, you can consolidate that expression. So if you are multiplying, you're going to add your exponents together. So 10 to the 2nd times 10 to the 3rd becomes 10 to the 2 plus 3, or 10 to the 5th. And you can also think about exponents as being helpful when you're dividing as well. In this case, if we had 10 to the 5th in the numerator and 10 to the 2nd in the denominator, you subtract your exponents. So this becomes 10 to the 5 minus 2, or 10 to the 3. So just keep those tips in mind, as they can be really helpful as you're working on some of the calculations problems in this class and in others. All right, so let's take a look at the problem itself. This is about primary productivity. And the narration reads, in a rice paddy in Southeast Asia, the insolation energy is 6 million calories per meter squared per day. The gross primary productivity, or GPP, of the rice is 0.012 grams per centimeter squared per day. And the respiration loss, symbolized by R, is 20%. We're also given the information that 1 gram of rice is equivalent to 1,000 calories. This particular problem has 4 parts to it. One of the things that I want you to think of when you're approaching any of these problems is you want to visualize what the scenario is, and then you also want to identify key vocabulary terms that come up. The expectation is that you're going to be able to quantitatively express some of the concepts that you've been studying in class. And you'll be doing that as we go throughout the year and also at the end of the year. So notice gross primary productivity comes up, respiration comes up, and then notice that we've got values with lots of different units. So we're going to take this one step at a time here. First thing, again, it's helpful to visualize the scenario you're talking about. So this is about a rice paddy. A rice paddy is essentially an artificial wetland. So you can see the people here, they're actually harvesting rice. It's a grain that grows when it is submerged in water, and it would be kind of equivalent to emergent vegetation that you've been learning about in freshwater ecosystems. Let's take the first part of this problem, and it asks us to calculate the NPP, or the net primary productivity of the rice. So if we're thinking about, here's our rice plant. The rice plant, or any primary producer, is taking sunlight, and through the process of photosynthesis is turning that into carbohydrates. So we're trying to figure out the net primary productivity. We know that even though the plant is taking in sunlight, some of that energy that it captures chemically, so sunlight turning into chemical energy, is going to be lost to the process of respiration. Remember, all organisms respire. Primary producers can both photosynthesize and respire. So we want to figure out how much is actually left over after respiration loss. So let's go ahead and kind of talk through that in terms of step-by-step approach. The first thing you want to do in any of these situations is you actually want to identify what you know. So one of the things that you should know from your content understanding is that net primary productivity is equal to gross primary productivity minus respiration. Okay? So it's an equation that you should know off the top of your head. From the problem, we know that gross primary productivity is equal to 0.012 grams per centimeter squared per day. And we also know from the problem that respiration is equal to 20% of the gross primary productivity. So in other words, 20% of gross primary productivity is lost to respiration. All right, well now we're pretty much set, right? We know if we can plug in GPP and we can plug in R, we can solve for NPP. So the first thing that we're going to do is we're going to take those values and we're going to plug them in. So we know that R is going to be equal to 0.2, which is the same thing as 2 times 10 to the negative 1. And we're going to be multiplying that by our GPP. So we have 2 times 10 to the negative first times 1.2 times 10 to the negative second. Remember, if you're multiplying values that are both raised to an exponent, we can add those exponents, and then we can just multiply the front numbers here. So this becomes 2 times 1.2 times 10 to the negative third. We haven't done anything with the units here, so we still have grams per centimeter squared per day. So this is our loss to respiration, is 2.4 times 10 to the negative third grams per centimeter squared per day. Now we have our R value. We can plug this into our original equation that net primary productivity is equal to gross primary productivity minus respiration. So in this case, that's equal to 1.2 times 10 to the negative second grams per centimeter squared per day, minus our loss to respiration of 2.4 times 10 to the negative third grams per centimeter squared per day. Notice because we have the same units of measurement, we can simply do math with these two numbers. It is a little easier if we get them into the same exponent since we're doing subtraction here. So I'm going to express this as 1.2 times 10 to the negative 2 minus 0.24 times 10 to the minus 2. So here again, we have some simple math to do. 1.2 minus 0.24, you can probably do in your head, is 0.96 times 10 to the negative 2. Critical that you have your units of measurement here, otherwise your answer isn't valid. So it's grams per centimeter squared per day. All right, we're ready now to move on to part B of the problem. So our original stem of question is still here. This is asking us to find the efficiency in percent of photosynthesis by the rice. This is how efficient is the rice plant right here at capturing the sunlight and using the process of photosynthesis to turn it into carbohydrates. So now we're looking at this part of what the plant is doing here. All right, so what does this entail? Again, with any problem, the first things that you want to do are identify the things that you know, either because you know them because of your understanding of the content or because they're provided in the question. Here, photosynthetic efficiency is going to be equal to gross primary productivity divided by solar insolation, or amount of sunlight coming in, times 100%, or sorry, times 100, because we're going to turn it into a percent. Our solar insolation is equal to 6 million calories per meter squared per day. We got that directly from the question. We know as well from the question that 1 gram of rice is equivalent to 1,000 calories. And we know that the gross primary productivity is 1.2 times 10 to the negative 2 grams per centimeter squared per day. So those are the pieces of information we need. Looking at what we need to figure out, we need to take gross primary productivity and we need to divide it by solar insolation. But you may recognize, if you look at the different colors here, I've tried to make them stand out for you, that our units of measurement are different. So this is a scenario where we're going to need to do some dimensional analysis to make sure that SI and GPP are in the same units. Once they are, we can then do some math with them to calculate photosynthetic efficiency. So there are lots of ways that you can approach this. I'm going to show you one way to do this dimensional analysis. I'm going to choose gross primary productivity, and I'm going to convert from grams per centimeter squared per day into calories per meter squared per day. You could go the other way around, and you could convert solar insolation into grams per centimeter squared per day. Either approach would work. So the first step I'm going to take is I'm going to multiply by a conversion factor of 1 times 10 to the third calories per gram. Now, where did I get that from? I got that from the information in the question up here. We know that 1 gram of rice is equal to 1,000 calories. So I made an equivalency. 1 gram of rice, that's the blue here, is equal to 1,000 calories, or 1 times 10 to the third calories. Notice now that my grams are in the numerator here and the denominator here, so they're going to cancel out. So now I've successfully gotten rid of grams and converted that into calories. I'm not done though, because I still want to convert these centimeter squared into meter squared. So I still have another step with my dimensional analysis. So the next thing I'm going to do is set up a conversion factor that will allow me to convert from centimeters squared per day into meter squared. Now remember, a centimeter squared is a tiny little measurement, a centimeter by a centimeter. And you need to know that there are 100 centimeters in every meter. So a meter squared is a meter by a meter, or 100 centimeters by 100 centimeters. So that's 100 times 100, or 10,000, or 1 times 10 to the fourth centimeters squared for every meter squared. Notice now my centimeters squared are in the numerator and the denominator, and those are going to cancel out, which means I'm going to have converted my GPP now into 1.2 times 10 to the fifth. So again, I multiplied across the top here, calories per meter squared per day. Now I can compare GPP and solar insolation because they are in the same units. So we can do the next step of our problem, and that is calculate our photosynthetic efficiency. So again, we're going to do our GPP, which we've now expressed as 1.2 times 10 to the fifth calories per meter squared per day. And we're going to divide it by our solar insolation. Remember, when you're dividing by a fraction, you're really flipping it over. And solar insolation is expressed in a way that we can express it as a fraction. So it's 6 million calories per meter squared per day, or 6 million calories over meter squared per day. I took that fraction and I flipped it over. So I'm multiplying my GPP by 1 over my solar insolation. Notice now, meters squared and meters squared are going to cancel out. Calories and calories are going to cancel out, and days are going to cancel out. I can check back to my original problem and notice I want to end up in percent, so that's okay. Once I've done that step, the next thing that I'm going to need to do is actually multiply by 100. I want to convert this into a percentage, so I'm multiplying by 1 times 10 to the second. Again, the reason I'm converting everything into scientific notation is it makes my math job easier. If you notice across the numerator now, I have 1.2 times 10 to the fifth times 1 times 10 to the second. So across the top, it's 1.2 times 10 to the seventh. I'm dividing that by 6 times 10 to the sixth. So what I'm left with is 12 divided by 6. And that's going to get me an answer of 2%. So my final answer here is 2%. So those were the first 2 parts of that problem. We're going to look in a separate video at the second 2 parts.